Hello, this is Ira, and today we're gonna go over a section from the thermodynamics section. We're gonna review the 193.007 heat transfer problems. So this one, it has only two knowledges, which is knowledge 01 and 06. And as long as we understand this, I think we're gonna be okay, and we're gonna be able to solve the problem. So the first one, it describes the different heat transfer mechanisms. So the first one is conduction, then we have convection, and we have radiation. So for conduction, right, I just like to summarize here like each one of them. But basically, conduction is the transfer of heat through a material, right, without any movement of the material itself, and it's gonna occur when, for instance, heat flows from one object to another, as we can see here. So we have this transfer of energy between the adjacent molecules from one object to another through a direct physical contact, right? That's what I say by direct contact here. That helps me remember that. So the rate of heat transfer by conduction depends on this temperature difference between the objects, right? So it's going to be a delta T between these objects, and also going to depend, for the thermal conductivity of the material and the distance between the objects. For example, a conduction, it can, for instance, in this one, we have a conduction of a hot stuff, right? If we touch the hot stuff, like, that's gonna be direct contact. Or if we hold a warm cup of coffee, depending on where we grab the cup of coffee, right? It's how we're gonna be able to transfer that heat. Like, if we touch it from here, we're gonna receive more heat from here, but we're gonna burn ourselves, right? So we're gonna have a higher conduction. It's gonna be hotter in that area. So the next one is gonna be convection. So for convection, heat transfer is gonna happen by the movement of fluids such as liquids or gases. So movement of a hot liquid, for instance, or a gas, and it's gonna occur when a fluid is heated and it's gonna expand and become lessen, it causing to rise and be replaced by cooler fluid. So convection can occur in both natural and forced forms. So natural convection occurs when there is no external force driving the flow. And, it can happen like in a pot of boiling water like here. Or forced convection occurs when there's like an external force driving the flow, like when we have a pump, right? So that's why we say that when we don't have the reactor coolant pumps running, we are moving the flow using natural convections, right? So now the last one is going to be radiation. So radiation is the transfer of heat through electromagnetic waves, right? So that's going to be radiation. Is like, for instance, the radiation that we get from the sun, right? We know that this radiation can travel through vacuum, so that's where we can get this radiation from the sun, for example. And it does not require any material or medium to transfer the heat. And for instance, like all objects emit radiation, and the rate of heat transfer depends on, the temperature of the object and the emissivity of the material. But radiation can occur at any temperature, and it is the primary method by which heat is transferred, like I mentioned, from the sun through Earth, right? So in other example of radiation, it can be like a heat radiating from a fireplace. So that also can be another example of radiation. So we're gonna use these three, and we're gonna see different examples on the problems. When we go over the problems, we will see that. So now, this other knowledge. So this is gonna be a little bit more simpler in a way. But we are gonna look at three formulas. We're gonna look at this, rate of heat equations, right? So for instance, we have the first one that is Q equal mCp delta T. So this formula, so we have seen this before, right? So we use this formula when we don't have a phase change, and we usually like this one like we use it like for sensible heat, right? Because there's no phase change. And we usually get to use this one when we have problems with heat exchangers, right? We will use this one like all the time. And when we go and review the heat exchanger problems, we're going to use this one like a lot. But then there's going to come times when, when latent heat is going to be involved, right? So when we have a phase change, right? So that's when we will use this one. And usually this one, it gets to be used when we have like these condensers and stuff like that. So we're gonna be able to use this one, but this one we're still gonna use it in like steam generators as well. And there's this other last one. So this last one, what is this one? And I think this one, it took me like a little bit longer to kind of like understand, but this one we use it to calculate, the rate of heat transfer, because this is our rate of heat transfer. But we're trying to calculate the rate of heat transfer between two objects, right? Because that's why we have this delta T. And it's going to be across a medium. That's why we have these physical properties. This U is going to be the thermal conductivity, and this is the area, right? And this formula is, I don't know if you have taken thermodynamics, but we use this formula from, or is derived from, Fourier law, and is used in many applications. So we're going to use this one a lot. So for example, say we want to determine that heat rate between like a room and the outside environment. This is the formula that we will use, right? And the delta T value, this value is going to represent the temperature that we have, the temperature difference that we have like between the room and the outside. That's what this delta T is going to represent. So everything is steady state condition, basically. We don't have to deal with any other thing other than steady state conditions. So that makes things very easy. And we're going to use these formulas. We're going to use them in different ways. The questions are going to be formulated in a way that, is going to challenge us a little bit. It's going to be very fun. I really like the questions. So then this other one, okay. This other one, goodness gracious. It took me a long time to understand. This is the one that actually it took me a long time to understand, because when we are talking about, this core thermal power, so when we have, this core thermal power here, we face the issue of determining, okay, from where is this core thermal power coming from, or this calorimetric that we call, which is this, or this heat balance power. It's known by different ways, right? It's known by this calorimetric, heat balance power, core thermal power. But this core thermal power is basically the heat rate in the reactor side, right? It's gonna be this heat rate in this reactor. So that's what basically this core thermal power is. But one of the things that, we need to kind of like use this heat balance equation here is we need to verify like what is coming in and what is coming out, from all this energy. How is this energy moving on the reactor cooling system, right? So if we are trying to get the heat inputs for that, what we'll have to do is to say, okay, what's coming in and what's coming out, right? So to me, it's like, okay, I need to figure it out what's coming in and what's coming out. So it says that what's coming in, I have the reactor core core thermal power or the heat rate from my reactor coolant pump, and the pressurizer, right? So I have the reactor coolant pump. This is what's coming in. This is what's coming in, right? And my pressurizer. So it goes like this. So it's basically what's coming in. So then what's going out, what's going on, it's going out from here to there to the steam generator. So that's what's going on. I have my letdown. So the letdown is going to be this part of the reactor coolant system where I move this water, the control volume system, where I have all my demineralizers and everything. So, but there are going to be things that we're not going to use here. We're going to remove because this is kind of like part of like another system. But also we have the ambient, right? What's like the outside? What's the heat transfer rate, right? So we're trying to consider like everything. Also the blowdown, right? We're gonna have this blowdown here. That's what's coming out because we have for the blowdown we have this the blowdown is is a system, and it's gonna be part of the reactor coolant system, and we use it to remove impurities. That's what is called the blowdown demineralizer, right? So, and it basically like it's trying to maintain the water chemistry within the range that it needs to be kept in order that we, keep the steam generator in good condition, right? We don't want any impurities in here. So that's what's coming out. That's why we say it's coming out. And the feed water, right? So this is the feed water goes to the steam generator, so it's not part of this. So it's part of the steam generator. So then what happens? So this is what the energy that we put in and the energy that we put out, and all of these must be equal. But I don't consider the letdown or the pressurizer heater in here, right? So what are the things that I'm not considering? The pressurizer heater or my letdown, right? So I'm not considering those things. So, but I'm gonna consider everything else, right? The one that I actually need to get is gonna be this one because that's gonna be my core thermal power, and I'm gonna have several questions that are gonna ask about that. So I'm gonna use this, the RCP, the reactor coolant pump, the steam generator, ambient temperature, blowdown, and feed water. So I'm gonna rearrange this. So I'm gonna end up with, the rate of heat transfer from the reactor. It's gonna be equal to the one on the steam generator, the one from ambient plus the blowdown, minus the one from the RCP minus the feed water. Okay, makes sense. So now, this is what I come up because there are so many Q's and so many letters, and it's confusing for me. So I know that my core thermal power is going to be equal to whatever I have heat from the steam generator, my blowdown, my ambient, minus my RCP, and minus my feed water. And I just need to remember that these ones are going to have a change. These ones have a change, right, in latent heat. They have latent heat, so I'm going to see a change in phase. So because of that, I need to know the formulas for this because I'm gonna be asked different questions, so I need to know what's affecting. So to determine the heat rate on the steam generator, I have the mass flow rate from my feed water, and I have my delta H, which is gonna be it's gonna be this one from the steam and the feed water, right? So I just grab this difference here. And those are the ones that I know I will be able to substitute in here. The ambient and the RCP, those ones stay the same, stay as is. So this is kind of like easier for me to remember. It helps me remember a little bit better, right? Like what's happening in here. Okay, so now I think we can just go over and take a look at all the questions, right? So now let's go over and take a look at all the questions. Hello, this is Ira again. So now let's go over the questions with the questions from the 183.007 heat transfer. So the first question is asking, it's asking the transfer of heat from the reactor fuel pellets to the fuel cladding during normal operations is primarily accomplished via what? So we have the heat transfer from the fuel pellet to the fuel cladding, right? These are the pellets, this is the cladding. So what's in between? We have something in between. What do you think that is? I think you already know the answer to this one, right? So for this one, and it's important to know this because we're gonna have another question related to this, but in this one, so it's talking about, the heat transfer from the reactor fuel pellets to the fuel cladding. Primarily, the heat transfer is via conduction. And the reason why is because, here what we have is helium. And helium is going to be a very, very small atom, right? And that's why we use helium, because we're going to use hydrogen. So we use helium, an inert gas, because one is going to be an effective medium for heat transfer, right? But also the gas is stationary. So since the gas is not moving, and that's where we need to pay attention, because we can say, oh, there's gas, it's fluid. Yeah, but it's not moving, remember? It has to be moving to be convection. So that's why in this case is conduction. Now, the next question, P584, refer to the drawing of a fuel rod and coolant flow channel at the beginning of the fuel cycle. I think this is just extra. So it's at the beginning. It can be at the beginning, at the end. It can be any time. So that doesn't matter too much, because this is the question, right? The question says, which of the following is the primary method of heat transfer through the gap between the fuel pellets and the fuel cladding? We already talked about this. The molecules in here are not moving, so is conduction, and it can be very, very confusing, right? We just need to remember that if the fluid is not in motion, is what? Conduction, correct. Okay, now this next one, during a loss of coolant accident, which of the following heat transfer methods provides the most core cooling when the fuel rods are not in contact with the coolant? So when we are talking about normal operations, we already decided, or we already figured out and determined that the heat transfer medium is gonna be conduction, right? So conduction during normal operations, because we already determined that from here, right? But if we have an accident, right? It says we have an accident. Which one of the following heat transfer methods provides the more core cooling? Well, fuel rods are not in contact with the coolant. So if the fuel rods are not in contact with the coolant, they cannot be this, because they're not in contact with the coolant, right? But they are also is not during normal operations either. So then what it is? Emission is not a form of so this one is not. It's not a form of heat transfer. So in this case, it's gonna be radiation, right? So the cladding temperature is gonna be very, very hot. So in this case, if we have a meltdown or whatever, the only form of heat transfer is gonna be through radiation, right? So also, even though if there's no meltdown or anything, but if the cladding is not touching the water because the water already evaporated, we have a loss of coolant accident, like it says, right? So the cladding is just exposed and is just emitting radiation at that point. The next one, P985, it says that reactor fuel rods are normally charged with what? We talked about that. We determined that they are charged with helium, right? With helium gas, which improves heat transfer by, do you remember, by what? Conduction, correct. So it's conduction. We already talked about it. When we have this helium, we don't have movement, right? The helium is stationary, so no movement. Okay, now the next one is P1884. A nuclear power plant is operating at 60% power. Is that even relevant? I don't know. Which one of the following is the primary method of heat transfer from the outer surface of the steam generator tubes to the bulk feed water? Do you see that? So what stays with me is this. The outer surface of the steam generator tubes to the bulk feed water. So for this one, so we're gonna have the first one is radiolysis. Like we didn't talk about radiolysis or anything like that. So no. So that's not happening. But what is happening in here? It says bulk feed water, right? That means there is water flowing, right? On the tubes, on the steam generator tubes. That it has to be flowing. It's just not stationary. We are generating energy. We need to move that water. The water is not going to be stationary like the helium and the fuel pellets. Like it's not going to be like that. So we know that we have fluid in motion. So that means that it's not radiation or conduction. So it's going to be convection, right? So now the next one, P2284. Okay, this one is asking, which one of the following describes a heat transfer process in which convection is the most significant mode of heat transfer? So this one is telling me, okay, check each one of them and tell me which one is convection. Okay. It says from the fuel rods to the core barrel during core uncovery. When do we have core uncovery? When we have the fuel rods uncover. When we have a LOCA, right? A loss of coolant accident. So we have all the rods uncovered. So then what happens? What's the only form of heat transfer in this case? So it's going to be radiation, right? So, okay. It's going to be radiation. Sorry, sometimes my pen is just not working properly. Okay, so now the next one. I just want to see which one is what, and then I will go back to the question because I just need to verify each scenario, right? So the next one is through the tube walls in a steam generator during a normal operation at 100%. Through the tube walls in the steam generator. So we already had a discussion, right, about the tube walls. So on the tube walls of the steam generator, what we're gonna try to say, okay, what's happening, right? It's between the tube walls. So We talked in normal operating conditions. All right, we're gonna have conduction, right? So then to me it's like, oh, okay, so we are operating normal operation, but it depends. It doesn't only depend like, oh, I'm operating normal. I know this is gonna be conduction. In this case, it is, right? Because it's only saying that the heat transfer mode is through the tube walls on the steam generator. It doesn't say, oh, there's fluid or there's a bulk, like it said here in this other question. It didn't say that, right? So that's why we just need to put attention to what this question is asking. Because if we are assuming, sometimes we have to assume, I know it's confusing, but in this case, it's just saying through the tube walls in the steam generator. So the only form of heat transfer in here is what? Do you guess this one? Conduction. Correct. So the next one says, from the fuel rods to the steam generator, 24 hours after a trip of all reactor coolant pumps. This one is interesting. It's very, very interesting. Remember what we talked about. So this one is interesting because it's giving us different things to think about. It says we have a reactor trip of all the reactor coolant pumps. If we have a reactor trip and we don't have the coolant pumps, we are having natural convection. Right? Remember that part? So if we have natural convection here, right? Well, it's convection, right? So we know that this one is gonna be convection, but is the one that is giving us the most significant mode of heat transfer? Well, we know this one is radiation, this one is conduction, that one doesn't count. Let's take a look at the next one. It says, now the next one says, from the fuel pellet center line to the fuel cladding during normal operation at 100% power. Okay, from the fuel pellet center line to the fuel cladding. Remember, we have helium here and it's not moving. So since it's not moving, what is the only form of heat transfer here? Is going to be conduction. So the only answer or the only possible answer here is going to be Charlie. The next one, question T2884, asks the following. Which one describes a heat transfer flow path in which conduction is the dominant mode of heat transfer? Now we need to determine of all these scenarios, which one uses conduction as a mode of heat transfer, right? So I think this is gonna be, fun as well. What happens again? From the fuel rod to the core barrel during core uncovery, we have radiation. So no. From the main turbine exhaust steam to atmosphere via the main condenser cooling water and the cooling water tower during normal operation. So if you don't know anything about nuclear, this is going to be very confusing, right? So the heat transfer between the main turbine exhaust, let's use another one. So we are transferring heat from the main turbine, right, to atmosphere. What's in between? So we're gonna have main condenser and we're gonna have cooling water. So this is what we have. So it's just so many things. So we're gonna have turbine, condenser, because this one eventually is gonna return to my steam generator, and then it's gonna feed into my reactor, primary, secondary. So this is my turbine. The steam that I get out from here I'm sorry, I'm not the best I don't do the best drawings. So this one is gonna go to the cooling towers, right? So that's what it's telling me, right? From the main turbine, exhaust steam, from here it goes to atmosphere via the main condenser. So that means that the main condenser is in between, right? So from here, turbine, main condenser, cooling tower, and then to atmosphere. Okay, I have all of this stuff happening here. So what is happening here? We said that this is gonna be considered a gas. It's a fluid, right? And it's in motion. It's going away. It's forming some beautiful, beautiful clouds outside the power plant. So pretty. All of this is moving and is forming these clouds. So the form of heat transfer in this case is gonna be, and I think you already guessed it, convection. I like this one. But this is not the answer because it's asking about conduction. So we have radiation, we have convection. Now, from the fuel rods to the steam outlet of the steam generators during a station blackout. Station blackout meaning like we are cut off power like from the outside. So from the fuel rods to the steam outlet of the steam generator. So from the fuel rods that are going to be here in my reactor to the steam outlet of the steam generator, which is going to be this part, right? What happens during a station blackout? During a station blackout, we lose the RCPs, the reactor coolant pumps that are going to be here. We lose them. What happens when we lose the RCPs? We don't have forced circulation, right? We have natural convection. So that means that this is not the answer, right? So no. Now, from a fuel pellet to the fuel cladding via the fuel rod, fuel gas during normal operation. And when we say gas, we might think, oh, it's in motion, but since the gas is helium and it's between the cladding and the fuel pellet and it's not in motion, that's why here in this case is conduction. So that's why answer D is correct. Okay, now let's take a look at the next one. Why is pool boiling in the tubes of a single-phase heat exchanger on the Saraball? Because the turbulence will restrict flow through the heat exchanger tubes, right? So, I mean, there are questions that they're not gonna come out, which is good. So now, this question, I think this one is interesting. This one is gonna be interesting. So, which one of the following pairs of fluids undergoes heat transfer in identical heat? Okay, again, which one of the following pairs of fluids undergoing heat transfer in identical heat exchangers will yield or will have the greatest heat exchanger overall heat transfer coefficient? So there are some things to know that air, water, and steam and oil in this case, they're gonna be a medium that is gonna be commonly used to distribute heat to process loads, right? However, steam is gonna be superior. It's gonna have many more advantages than hot air or hot water. So to me, steam is like the best. So steam has the heat carrying capacity that is greater than air or water, right? Also, it provides like its own locomotive force and also provides heat at a constant temperature, which is also important, right? So steam is the best thing, right? But since air and water, I mean, what's the closest to steam? Before steam, what do we get? Hot water, right? So it's gonna be the closest thing like to or water. We're gonna be able to transfer heat very, very well between these two. Air, right? It's not gonna be so much. We know that it's not as good. So steam is gonna be like, the go. But the comparisons that we have is water to water. We know that's a no because we know steam is superior. Here we don't have steam. We know that air is not as good. So this one is not. Also, oil is not gonna be as good as steam. So we only are left with steam and water. And there's gonna be like a couple examples similar to that, like which one is the lowest. Like the lowest is gonna be air to water in this case. So I think there's just only those two questions. So it's just a matter of just knowing that. Okay, so this other question is P3084, and it states that a nuclear power plant is operating near 100% power. Main turbine extraction steam is being supplied to a feed water heater. Extraction steam parameters are as follows. So it's giving us the steam pressure, steam flow rate, and steam enthalpy. The extraction steam condenses to saturated water. So we have a phase change, right? And then leaves the feed water heater via the drain line. What is the heat transfer rate from the extraction steam to the feed water into the feed water heater? So we just want to know like the difference in here. We're gonna get our delta H basically. So this is the formula that we're gonna use from the feed water. So this is feed water for the feed water. This is gonna be for the steam, and this is gonna be for the feed water. So for the steam pressure, if we are giving, so we know the steam enthalpy. So the steam enthalpy is gonna go here. But what's the enthalpy for the feed water? So since they're giving us the steam pressure, we just need to go to steam table and look for this value on our steam table. And we will get this on the liquid because we're giving a liquid mixture and then the gas. So we get the one from the liquid or the fluid. And we end up getting this formula. We just plug and play and we just end up getting this formula. I'm sorry, we end up getting this value, which is C 5.4 times 10 to 8. The next one. So the next one is question P3384. So this one is going to be different, as you can see here. So this one, it states that a nuclear power plant is initially operating at a steady state power level with the following main condenser parameters. Main condenser pressure, 1.2 psi. I just go to the steam table and I just got out my Tsat at that temperature. Then I have my cooling water inlet and my cooling water outlet. So this is the turbine exhaust. This goes back to my steam generator eventually. And this is my cooling water in, cooling water out. And this is my condenser, right? Okay, so they are giving me this. But what I'm trying to determine like the temperature difference between here and here. So I'm giving the pressure of this my condenser, so I can gather the temperature from here because it's telling me, okay, due to increased condenser air in leakage, the overall heat transfer coefficient of the main condenser decreases by 25%. So I'm not very efficient right now because I had a leakage, right? So I have a leakage here, and I'm 25% less efficient, meaning that I am only efficient at 75%. Before that, I was at 100% efficient. Now I'm 75. That's what it's trying to tell me. Now, main condenser heat transfer rate and cooling water temperatures are unchanged. Which one of the following is the steady state main condenser pressure resulting from the reduced heat transfer coefficient? Okay, so I need to get the pressure reduction from this. So the things that I know, right, as I mentioned, so I know from here, I know the pressure from here. So since I know the pressure, I can gather the temperature, and I can gather delta T, a temperature difference between here and here. From this one, I just gather my average, right? And what else do I have? So I have this formula because we're talking about my overall heat transfer coefficient. We know that Q is equal heat transfer times my delta T. I end up with, this formula. Basically, I just end up with this formula right here because I cancel this out. Is the same. So delta T equals 0.75 times delta T. So I just plug and play. And I'm gonna get from here the temperature of my exhaust is gonna end up being 120 Fahrenheit. That's gonna be the final temperature because I saw this temperature change, right? So my new temperature is gonna be 120. So now, if I go to the steam table, I look for the saturated pressure at this temperature, I'm gonna get 1.7 psia, right? So because I'm larger, I need to be lower in order to be more efficient. I need to be closer to vacuum, right, to be more efficient. So I was being more efficient at 1.2 psia. I have an in leakage. My pressure obviously increased. So that's why I'm getting this value, but I need to go to my steam table, right, to determine the pressure. But as long as I get the temperature, I can go and get my pressure. Okay, this is a similar question from the previous one. This is also a similar one. This one states P585 during steady state power operation, core thermal power can be most accurately determined by multiplying the total mass flow rate of what? When we talk about core thermal power, the things that are important for core thermal power are going to be the pressure of the steam generator, temperature of feed water, and the mass flow rate of the feed water. Those are going to be the important things. So this one is telling me that core thermal power can be most accurately determined by multiplying the total mass flow rate of what? It gotta be the total mass flow rate of my feed water. So feed water. And what's affecting that, right? What's affecting that the most is gonna be the change in enthalpy on my steam generator, right? So yeah, it's gonna be the change in enthalpy. I think that's my formula. If you remember the formula that we use when we have a phase change, so that's gonna be it. So now we have this other question. This is gonna be just a ratio. So P 785, it states that a reactor is currently producing 200 megawatt of core thermal power. Reactor coolant pumps are adding an additional 10 megawatt of the thermal power to the reactor coolant system. The core is rated at 1330 megawatt. So this is what the reactor is supposed to be, but this is what I'm producing. And this is a part that is just making things like, oh, the RCPs are adding this blah into the reactor coolant system. Yeah, no, what I need to know is like basically what is the measure and what is the current, right? And what is the rated. And the way to get my core thermal power is just like a ratio of my actual over my rated. And that's gonna give me a 15% in here. Just don't be confused by this part in here. Okay, so the next one, it's gonna be P137. So for this one, P137, so we have, so this is the other one that I was talking about. This one's, we're gonna use this formula, right? This formula for my CTP is that it's gonna be equal to my steam generator, and stuff like that. So that's kind of like the formula that I'm gonna be using for it. So it's gonna be question P137. So the power range nuclear instrument is being adjusted to 100% based on the heat balance calculation. So this is a heat balance calculation. What it says here is just like adding words, but important here is to know is based on heat balance calculation. That's why we know we're gonna use this one. Which one of the following will cause indicated reactor power to be greater than actual reactor power? Okay. So if the reactor coolant pump heat input term was omitted from the heat balance calculation, so if we omit the reactor coolant pump here, right? Overall, we will reduce this part. So the CTP will be lower. So the feed water, flow rate used in the, so because if we remove that one, oh wait, is minus RCP, so no, I had it wrong. So if I remove that one, so I'm going to use this formula. So if I remove this one, my CTP is going to increase. Can you see that? Okay, so now the feed water flow rate used in the heat balance calculation was lower than the actual feed water flow rate. So if the feed water flow rate in the heat balance calculation is lower, it's like this. This one is lower. I mean, we won't have like a significant change probably. I mean, it's affecting both sides. And now the steam pressure is used in the heat balance calculation was 50 psia higher than the actual steam pressure. So that means that is affecting pressure, temperature. So it's gonna affect this item here. So that's gonna make it lower, right? Because it's affecting this part. Because it's talking about the steam pressure, right? It's gonna bring it down. So now the enthalpy of the feed water was miscalculated to be higher. So the enthalpy of the feed water is higher, right? That will bring it lower overall. So the only possible answer here is gonna be A, right? The reactor coolant pump heat input term was omitted from the heat balance equation. So That's what we need to do for all of them. Like when we get to these questions, we need to evaluate each one and what is happening. We can either use this one and we can also use this one, right? To see what's happening in here. Just this one is minus. Okay, so now for this problem, we will actually go over a couple of them just to make sure that we understand the concept of this heat balance equation. So how we're gonna work around with the heat balance equation. Remember, this is like the main formula, but what I do in here, and let me just think this is wrong. So this is the correct formula here. Okay, so this is how I'm gonna, develop this formula. So I'm just gonna mark here what goes with what. So this is from the steam generator. This is what we're considering. We're using mass flow rate from the feed water and the blow down and the enthalpy of the steam. For the blow down, we have the mass flow rate and the enthalpy of the blow down. We have the ambient heat transfer, and that's kind of like on the positive side, like what we're gonna be kind of like adding to it, right? And then what we're gonna be removing from it is gonna be this part, and I think that makes it a little easier to kind of like remember. So the RCP is gonna be this part, and the feed water is gonna be this other one here. So that way we can see, this one is this one expands into this one, this two stay the same, and the feed water heat rate expands into this. That's how we actually calculate those ones. Okay, so now what we need to do is take a look at each one of them like separate, and I'm just gonna, because this one is, I should have put the mass flow rate instead, but I'm gonna grab this one because this is the one that I'm gonna use, because what I need to do is like, okay, actually I might not need it. What I need to check is like, okay, what is this asking me to do? Okay, so let's go over this one, which is question P384. For this question, is telling me that the power range nuclear instruments were just adjusted to 100% power as determined by a heat balance equation. Okay, so first it's telling me, okay, I need to use a heat balance equation, which is gonna be this part, right? So remember that we talked about like heat balance equation, heat transfer in and heat transfer out has to equal, right? And for what comes in, I have the heat rate from the reactor plus the heat rate transfer from my reactor coolant pumps plus the heat rate from my pressurizer. And that's going to be equal to what's going out, which is the heat rate from my steam generator, right? Because that's going out to my turbine. It's not what's coming in to my reactor. So this was going out to my turbine. So that's what I'm using to determine that. So I also have my Q from the letdown, which is part of my reactor coolant system, my control volume system, where I put all my coolant basically, and also like the ambient plus the blowdown. Remember that we talk about the blowdown, how we use it like kind of like clean some part of my steam generator, so we don't have like anything, so it keeps everything clean basically, and it removes impurities and it keeps the chemistry and whatnot. So that's why we have the blowdown. So this is when they talk about that heat balance calculation, this is what they're talking about. But remember that I previously mentioned that for that we don't need to use this one or the let down, so we're not going to be using those ones. So we end up only using, so I'm just going to delete this one. We don't need it. We don't need this. So we just end up using this part here, right? But then if we need to solve, right, because what we need to do is in order to, so from where is the core thermal power coming from? It's going to be coming from all the heat generated in my reactor. So that's going to be my core thermal power right there. So that's how we end up like calculating like the reactor power from here. Okay, so now that we have that relationship, so then what I do is I have to move this RCP to the other side. So I move it to this other side. It's gonna be minus the heat generated from the reactor coolant pumps. So and I have something like this, right? I have my CTP, which is this part called my heat balance equation for my power, my reactor power, my core thermal power. So this is gonna be this, right? And I know that on the other side I have the heat rate from my steam generator plus my heat from the blowdown. And I have my heat from the ambient temperature, which is actually positive. I don't know, did I delete this? Okay, so that's positive. So plus the ambient. So I got those three that are positive, and it's minus the feed water here. But then I have to move the one from the RCP to this other side, so that's also like a negative. But if I want to see exactly what's inside of each one of these, right? As I mentioned, these two stay the same, the ambient temperature and the RCP. They're going to stay the same. But I can expand what's happening on the steam generator. So this part, which expand on this one, it basically stems from this heat rate generator on my steam generator, right? So what I'm gonna do is my steam rate from the steam generator is basically this, is the difference on the mass flow rate from my feed water and blowdown, and then I multiply that times the enthalpy of my steam, right? Because that's what kind of like it's coming out, steam is coming out, so that's why I have to use enthalpy from the steam. Whereas on the feed water part, I use the enthalpy of the fluid. This is gonna be a little different. So when we go over this example, it's just gonna be a little different because of that. And also the blowdown is, we have mass flowing. So that's why we use this mass flow rate of the blowdown times the enthalpy of the blowdown here. Okay, so now that that's clear up again, let's go over and review this question again. It says, the power range nuclear instruments were just adjusted to 100% power as determined by a heat balance equation. So we already determined. So this is what I need to know. And I always try to remember this so I can expand into this, right? This is my mnemonic. This is one that helps me expand and remember how to expand into this one. So I have this as determined by my heat balance equation. Now it says, which one of the following would result in indicated reactor power being greater, right? So which one will give me a greater reactor power than the actual reactor power? So we're just comparing them a before and an after, basically. That's the way that I like to see it so I can understand what's going on. So now let's analyze what's happening. I just want to go over each one of them and see what's happening first before I can draw a conclusion. So I can just draw my conclusion at the end. So let's go over this one. So this one, it says that the feed water temperature used in the heat balance calculation was higher than the actual feed water temperature. So basically it's saying that the temperature of the feed water increased, right? So we had an increase on the feed water. What is that affecting? So this is the information that I have. So I don't see a temperature here. So I'm like, okay, I don't know what to do. But remember, if we go to the steam table, so let's go to the steam tables. If we get a temperature, remember the temperature in this case is increasing. They already gave us a temperature, and from that temperature provided, this is going to be way higher, but let's say from that temperature provided, we can go and determine the enthalpy, right? And this is gonna be for saturated vapor because we have steam, right? So it's gonna be the enthalpy of the steam from saturated vapor. So what's happening if we increase the temperature? So this is how we are increasing the temperature. So what's happening to the enthalpy? So the enthalpy of vapor increases. So we increase the temperature. Oh, but wait, it says that it's for the feed water. So for the feed water, we're looking at a fluid, right? Because we don't have steam in the feed water. It's feed water. It's already telling us what it is. So it's saturated liquid. So then let's just go back. Let's take a look. If we increase the temperature, what's happening to this, right? To the enthalpy of a saturated liquid. Okay, if I increase my temperature, what's happening to my enthalpy? I increase my enthalpy. Okay. Fair enough. So I'm increasing my enthalpy. So now I can relate that to the formula, but I'm not gonna get to a conclusion just yet. So I'm just gonna go over this formula here and say, okay, I know I'm affecting this part is increasing, right? And remember that we have this divided here. Imagine that we are doing x minus y. CTP, it's equal, all of this is x and all of this is y. So it's x minus y. So what happens if I have, for instance, this, I have a 10 minus a 5, it's going to be 5. What happens, right, when I increase this one? If I increase this one, it will be a 6, right? Which will bring my CTP to be lower, right? So in this case, I know that my core thermal power is going to decrease, right? It's just I'm trying just to simplify things, right, for me. So I know what's happening here. My core thermal power is gonna decrease. So now I go to the next one. It says that the reactor coolant pump heat input term was omitted from the heat balance equation. So I'm omitting this term, right? So let's go over again. CTP equal x minus y. If I remove this term from here, what's happening? Let's say that this one was 5, but if I remove this one, what's happening, right? Because this one is basically decreasing, right? I'm decreasing my terms here. So that means that this can be a 4. That will bring my core thermal power to increase it. So my CTP will increase, right? Because I'm removing this part. And I just pick random numbers to do that. It helps me. Okay, so now for the feed water flow rate used in the heat balance calculation. So now we're talking about the feed water flow rate. Okay, using the heat balance calculation was lower than the actual feed water flow rate. Okay, so I'm decreasing the flow rate on my feed water. So I'm decreasing this term and I'm decreasing this term, right? So I'm decreasing both, but in this one, the reduction here is even more because I'm also decreasing, removing the flow from the blowdown. So that means that my core thermal power gets lower, right? Even though I'm also lowering from this other side. Now, for the last one, it says that the steam pressure used in the heat balance calculation was higher. So we are increasing the pressure of the steam. So what is that affecting? So that should be affecting steam. So we have enthalpy of steam. So we go to the steam tables. Again, we're giving a pressure. Remember, we're giving a pressure. If the pressure increases, what's gonna happen to the enthalpy of steam? My pressure increases. The enthalpy of steam is gonna be increasing as well, right? So well, let me go over here because here is where things might change. So, I mean, this steam table, so if we go to like the actual steam table and we looked at values, so you can see here it's increasing, right? In this part, but we're having like those low temperatures. But if we look at the steam table, that is on in our, for instance, if we start like at a temperature of 160 Fahrenheit, right? These are very low temperatures. So when we are gonna be operating the reactor, obviously we're not gonna be operating the reactor in those very low temperatures. So that's gonna change actually. So we need to go over and look like a higher temperatures, right? Because otherwise we're gonna deduce from here, or deduction is gonna be, oh, it's also increasing, but we just need to remember, okay, it's gonna, the changes that we're gonna see are gonna be at a higher temperature. So if we go to our actual steam table, using the properties of saturated and superheated steam, which is the one that you're given. Usually is the one that you're giving from the DeRosa printing company. So from that one, you're gonna go to page 6, right? And you're gonna start seeing a change on the so if you increase the temperature or pressure of your system, you're gonna see that the saturated vapor, your enthalpy saturated, is actually gonna decrease, right? So that's one of the things to consider and to look for, like just to pay attention, right, to that, because otherwise you can get confused. So this one is decreasing. So let's say again, just for the sake of doing this exercise, this is what we have initially. So if this side decreases, I can say 9 to 5, it's going to give me 4. What is happening to my overall core thermal power? Well, it's also decreasing, right? So core thermal power is decreasing, so it's affecting my enthalpy of steam, which is decreasing. Okay, so that's good. Now I have analyzed all of them. Let's go back to the question. So the question was asking which one of the following would result in indicated reactor power being greater than the actual reactor power. So which one of the which one has like the highest, basically which one has a high CTP. That was asking for basically greater, higher CTP. So we go and we say that is Bravo, right? Since we already did the analysis, we performed the analysis, so we can determine that. Let's do another one, just because I think that this one for sure is like if you have to, for whatever reason, which I don't think it happens, for whatever reason you have to take this exam, this one is gonna come in the exam for sure. So now, and just let me bring this one because the other one was not correct. So I will bring this one down here with me. Okay, so this one is gonna be a little different. I mean, we analyze it. We might have like some different options, but it's basically the same. So it's gonna be questions P1384, and it states a secondary heat balance calculation. So we know heat balance calculation. We're gonna use this one. Is being performed at 90% reactor power to calibrate the reactor power instrumentation. It can be at any reactor power that we want. We just need to make sure that we analyze this equation. It doesn't matter if it's just 80, 60, 90, just don't get confused with that, right? So now it says, which one of the following will result in a calculated reactor power that is less? So the CTP is gonna be lower, so because we are comparing, right? So that is less than the actual reactor power. Okay, fair enough. So now we can just go and try to solve this one. The first one, the question is asking, or is telling us it says that the steam generator pressure indication is 20 psi greater than the actual steam generator pressure. Basically saying that I had an increase in my pressure on my steam generator side. If I go to my steam table, I notice that is affecting my enthalpy of my saturated vapor, and that is gonna be lower. And if we put that information in here, trying to do the math that we were doing for that, we will find that this one is getting lower, so that's gonna reduce my core thermal power, right? So I will have a core thermal power which is gonna be low. Okay, so now the next one is gonna be interesting, and for this one I just want you to remember this, just don't complicate yourself. This one is telling that the steam generator water level indication is 3% less than the actual steam generator water level. So when we talk about the steam generator here, we don't have anything related to water level. So when they talk about water levels, that's not gonna be affecting our reactor power, right? Meaning that our CTP will like stay the same, right? It will just stay the same because we're not affecting anything. So the before and after is just basically the same. So just remember the water level. That's gonna be important. Water level is not affecting the reactor power from, to calculate my core thermal power. Okay, now let's go to the next one. The next one says that the feed water flow rate indication is 3% greater than the actual feed water flow rate. Okay, so we are talking about the feed water flow rate, right? That is greater. So in this case, any change that we would do here is going to be greater on this side. So that means that our core thermal power in here, if we do our math correctly, it's gonna be greater, right? From before and after, right? But you can see that. That's very straightforward because it just goes directly into the mass flow rate for feed water. Now, the next one, it says that the feed water temperature indication is 20 degrees Fahrenheit less than actual feed water temperature. We translate that, it says that the temperature of the feed water decreased. So we don't have any temperature, but we need to go back to the steam table, right? And we need to take a look at the enthalpy for feed water. So if we decrease that temperature for the feed water, or enthalpy for fluid, it's going to decrease, right? So we're gonna decrease the enthalpy of the fluid, and that's actually going to affect only this side. So if this side decreases, that means that we are increasing our core thermal power. So on the first one, if the steam generator pressure indication is greater, the CTP is lower, right? And that's what we want, and it has to be less than the actual reactor power. So the answer for this one is going to be A. And we're going to have several examples. Example P2185, example P2485 is going to be similar. Example P2685 is going to be similar to it. Example P2885 is going to be similar. Example P3944 is going to be similar. But then we come to this other one. And I think this one is interesting because we just need to make sure that we understand what this question is asking for. Okay, so this question is P5044, and it states that two of the parameters listed below are used for calculating core thermal power using the standard heat balance method. So we have the standard heat balance method, and I wrote it here already. It says, which one of the following identifies the two parameters, right? So the first one, it says the reactor coolant mass flow rate. So here I have the mass flow rate from my reactor coolant system. The second one is giving me the option for temperature of the feed water. And if we remember the temperature of the feed water, it gives me the enthalpy, right, of my feed water. And already I can determine that from this information. Now here is giving me the steam generator pressure. So the pressure of the steam generator, it gives me the enthalpy of the steam, right? And then we have the steam generator water level. And remember that we talked about that this one doesn't affect our core thermal power, right? So now it's telling me that there are only two parameters that are used for calculating core thermal power. And yes, there are two parameters, but if I go over the reactor coolant mass flow rate, that's not the same as the mass flow rate of my feed water, right? That's gonna be different because one is gonna be so the mass for my reactor coolant system is gonna be kind of part of my. So let me just draw this steam generator here, right? Then I got, this is a little slower, but this is my steam. Then I have another system here, and this one goes to my reactor. I have my RCPs and whatnot. So that's what I have there. And the reason that we don't count, remember when we removed the letdown from our system, because that was part of the control volume system. That's the part that is feeding this part in here to make sure that we cool the water. So this one is hot leg and this one is cold leg, and this like the steam that we send to the turbine. Yeah, my drawings aren't the best, but you get the idea from that, right? So that means that the flow rate, I mean, it's not part of this formula, that flow rate from my reactor cooling system, because it's part of my primary. So this is not gonna be part of this. So this is not gonna be part of my core thermal power heat balance equation, right? So we just need to find the ones that we use. So we use these two parameters with water temperature and steam generator pressure. So the ones that says yes are these ones. So we know that the answer is gonna be Bravo on that one. And everything else is gonna be basically the same, except, so I want to just go over one question. I just want to go over this one, which is P6844, because everything else is going to be the same. So this is the last one that we're going to review for this. So P6844, let's talk about this one. This one is stating that when performing a heat balance calculation, so we're using again a heat balance calculation, we're using this to determine the core thermal power, right? That's what we're trying to determine. The measured thermal power is, so what is the value associated with the reactor coolant pump? So if I go to this formula, remember, and I don't know why this one is like that, but remember that we separated these ones. These ones are adding, right? These ones are removing, right? So the value that is associated with the reactor coolant pumps is a negative value, right? A negative value. And the adjustment is needed. Why? Why do we need to adjust it like that? Okay, this is the thing. Let's go and recap what a reactor coolant pump does. So the RCP, we use it. And remember, I'm just gonna make another mediocre drawing. So we have our reactor, we have our loop, we have my RCP, right? And then I have my secondary, I have my steam generator. So turbine, hot leg, cold leg. Okay. So this one is just basically trying to, remove that heat transferring to the steam generator. But okay, so the primary function of the RCP, the reactor coolant pumps, it's gonna be to circulate this, like the coolant, right? That's why it's reactor coolant pumps, because its function is to circulate. What a pump does, it pushes, moves the energy. Okay, so that's what it does. So, and it does it through the reactor core to remove the heat generated in the reactor, the heat generated by nuclear fission. So the RCPs, they use an electric motor, right, to be able to have that flow of energy here, creating this flow of coolant through the reactor core. So the kinetic energy of the coolant flow, so the kinetic energy, just gonna use this color. So the kinetic energy of the coolant flow is gonna be converted into thermal energy, right? Kinetic energy, meaning like the movement, is gonna be converted into thermal. How? It's gonna be converted into thermal because the cool water, is gonna pass through the reactor and it's gonna get heat. It's gonna get heated, right? Because that's where the fuel rods are gonna be here very, very hot in this part, because this is where fission occurs, and this water is gonna get warm, right? So that's how in a pump we convert kinetic energy to thermal energy. So This coolant is gonna absorb this heat generated by this fission reaction, and as a result, it's gonna increase the temperature, right? Which is gonna transfer the thermal energy to this humongous heat exchanger, which is our steam generator. And then it's gonna convert this thermal energy of the coolant into steam, which uses this turbine to generate electricity, right? So that's kind of like the process. So this is the important thing to remember. The RCP are going to convert this kinetic energy of fluid moving through this piping system of the primary into thermal energy. So I know that the adjustment is needed because, it's right. The flow of energy added to the reactor coolant by the RCP is converted to thermal energy of the reactor coolant pump. So, but here is giving me two options of nearly all or a small fraction. I have to convert nearly all because that's how I make money. That's how I generate electricity. Because if I were to convert it only a small fraction, we will be out of business, right? So we need to convert nearly all of the kinetic energy to thermal energy. That's what makes sense. So my answer is going to be nearly all. And the measured thermal power, the value associated with the RCPs is going to be negative, so meaning it's going to decrease. So my answer for this one is going to be alpha. So I hope this makes sense, and I hope this helps you understand a little bit more about how a reactor works. Thank you.